Diving into the world of machine learning, one term you'll frequently encounter is hyperparameters. Unlike parameters, which the model learns during training, hyperparameters are set before the training process begins. They play a crucial role in controlling the learning process and can significantly impact the performance of your model. Mastering hyperparameter tuning not only boosts model performance but also unlocks the full potential of machine learning algorithms. Stay tuned as we delve deeper into tuning methods and best practices. So, let's get started. Hyperparameters are the unsung heroes of machine learning, guiding the learning process from the shadows. Unlike parameters learned during training, these settings are chosen beforehand, shaping the model's ability to learn effectively. Their correct adjustment can be the difference between a mediocre model and a stellar performer. In the world of machine learning, hyperparameters play a crucial role in model success. They're like the secret ingredients that, when adjusted correctly, can significantly enhance a model's performance, ensuring it not only learns well but also adapts seamlessly to new, unseen data. This fine-tuning process is essential for preventing overfitting, a common pitfall where models perform well on training data but poorly on new inputs. Let's explore how to leverage hyperparameters for the ultimate model optimization. Learning rate, batch size, epochs, and regularization form the core quartet, each playing a vital role. The learning rate dictates the steps towards accuracy, batch size, and epochs harmonize the training's tempo, while regularization ensures the model remains versatile and robust. Understanding these hyperparameters is key to orchestrating a successful machine learning symphony. In machine learning, the learning rate is the step size during model training. It's crucial for efficiency. Too high and the model overshoots, never stabilizing. Too low and training crawls, wasting time and resources. The goal is finding the sweet spot, where the model learns fast without compromising accuracy. In the realm of machine learning, the concept of epochs plays a pivotal role in model training. Each epoch represents a complete pass through the entire dataset, influencing both the duration of training and the model's ability to generalize. However, a higher number of epochs isn't always beneficial. It can lead to overfitting, where the model excels on training data but fails on new, unseen data. To combat this, early stopping emerges as a crucial technique, halting training when improvement stalls on a validation set, thus preserving the model's generalizability. In machine learning, the choice of batch size plays a crucial role in the gradient descent process, impacting both the model's training efficiency and its performance. Larger batches provide more accurate gradients, leading to stable but memory-intensive training sessions. On the flip side, smaller batches, though less accurate, offer a more memory-efficient approach by leveraging noisier gradients to potentially escape local minima. Hyperparameter tuning stands as a cornerstone in machine learning, aiming to refine the algorithm's parameters for peak performance. It's not just about tweaking, it's a systematic search for the ideal settings. Grid search is a thorough method used in machine learning to find the best combination of hyperparameters for models. It systematically evaluates every possible combination, ensuring the optimal set is identified. While effective in discovering the most efficient parameters, this approach is computationally demanding. It's like searching for a needle in a haystack, but with the right tools and patience, the optimal set of hyperparameters can be found, paving the way to enhance model performance. Unlike the exhaustive grid search, random search adopts a more dynamic approach to hyperparameter tuning. By randomly selecting parameters to test, it efficiently explores the vast, high-dimensional spaces of potential model configurations. This strategy not only saves time, but often uncovers superior models by balancing the exploration of new areas with the exploitation of promising regions. With random search, we can achieve better model performance with significantly fewer iterations, making it a smart choice for optimizing machine learning models. Bayesian optimization represents a cutting-edge approach in the realm of machine learning, designed to find the best parameters for an objective function with remarkable efficiency. By constructing a probabilistic model, it approximates the function's landscape, using this insight to predict optimal hyperparameters. Its secret weapon, the acquisition function, smartly navigates the balance between exploring new possibilities and exploiting known good ones. Now, let's talk about some of the best practices and quick tips. In the journey of machine learning, beginning with the manufacturer recommended settings is more than a step, it's a strategy. This approach ensures that we're not flying blind, but rather starting from a point of informed strength. It allows us to gauge the current performance of our models accurately and set clear, achievable benchmarks for any adjustments needed down the line. In the world of business, the iterative adjustment and gradual refinement process stands as a beacon of efficiency. By making small, incremental changes and closely analyzing their outcomes, businesses can guide further adjustments with precision. As we delve into the intersection of artificial intelligence and leadership, it's clear that AI is not just a tool, but a transformative force. AI's ability to analyze vast datasets and predict outcomes is revolutionizing decision-making processes, enabling leaders to make more informed, strategic decisions. In this new era, leaders who embrace AI can anticipate trends, mitigate risks, and seize opportunities with unprecedented speed and accuracy. The future of leadership is here, shaped by AI's profound impact on how decisions are made and strategies are crafted.